November 18th, 1942, South Pacific, coordinates classified. Lieutenant Commander Joseph Wylie stood in the plotting room of the destroyer USS Fletcher, 3 decks below the bridge, surrounded by what looked like an impossibly complex clockwork mechanism weighing over 3,000 pounds. The Mark I fire control computer hummed with the movement of hundreds of gears, cams, and electrical servos, calculating mathematics that human minds could not process quickly enough to matter. Above him, the Mark 37 Director swiveled on its mount, tracking a formation of Japanese G4M bombers approaching at 280 knots from bearing 090. The optical rangefinder measured the distance. The radar confirmed the altitude. The stable element compensated for the ship's roll and pitch. All of this information flowed electrically into the machine Wylie monitored, and the machine performed a calculation that seemed impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. It predicted where those aircraft would be 15 seconds into the future. The 5-inch guns elevated to an angle that seemed wrong, pointing at empty sky ahead of the bombers. Wylie watched the mechanical integrators spin, calculating the ballistic arc of shells that would take 13 seconds to reach 35,000 feet. The computer added corrections for wind, for the Magnus effect of the spinning projectiles, for parallax because the guns sat 80 feet from the director. It calculated the lead angle, the elevation, and the fuse time, all continuously, all automatically. The guns fired. 13 seconds later, shells exploded exactly where the bombers arrived, exactly as predicted. One aircraft staggered, trailing smoke. Its right engine shattered by shrapnel from a burst that detonated 70 feet away. The bomber had flown directly into destruction computed by a machine before the shells had even left the barrels. What the Japanese pilots could not know was that American gunners had stopped, aiming at where aircraft were. They had begun aiming at where aircraft would be, calculating futures with precision that exceeded human capability. The transformation had required years of development, thousands of hours of engineering, and the creation of mechanical computers more sophisticated than any civilian calculating machine in existence. But by late 1942, American destroyers and cruisers carried fire control systems that represented the cutting edge of predictive ballistics. The problem that necessitated this technology was fundamentally one of time and motion. December 7, 1941, Pearl Harbor. As Japanese aircraft screamed through tropical skies, American gun crews fought back with 5-inch naval guns that represented the primary long-range anti-aircraft weapon in the fleet. Each shell required manual fuse setting. A sailor would turn a wrench against a clockwork mechanism, setting a timer that would, theoretically, detonate the shell near an enemy aircraft. The mathematics were unforgiving. Optical rangefinders had to calculate exact distance to targets moving at 300 miles per hour through smoke, clouds, and battle haze. Height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Fire control personnel had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor then manually set the clockwork time fuse. The shell was loaded, the gun fired. The fuse mechanism counted down. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft under these conditions were approximately 1 in 2,500 rounds, fired under ideal circumstances. In combat, with multiple targets maneuvering through defensive fire, the odds became catastrophically worse. At Pearl Harbor, itself, the inadequacy was laid bare in brutal fashion. American gunners fired thousands of 5-inch rounds at attacking Japanese aircraft. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all. Others fell back to earth, their contact fuses still armed, crashing through roofs in Honolulu 9 miles from the harbor. 68 civilians died that day. 32 of them were killed not by Japanese bombs but by American anti-aircraft shells landing in the city. The tragedy illustrated with horrifying clarity the inadequacy of existing fire control methods. The fundamental limitation was prediction. Aircraft did not fly in straight lines during attacks. They jinked, climbed, dove, and turned. Traditional fire control methods required gunners to estimate future positions based on observed present motion, but by the time those estimates were made, calculated, and set into fuses, the tactical situation had changed. The shells exploded in empty sky while aircraft flew through unscathed. The British had recognized this problem during the Battle of Britain. German dive bombers attacked at speeds and angles that made traditional anti-aircraft fire nearly useless. Fire control directors could observe where aircraft were, but could not predict with sufficient accuracy where they would be seconds later when shells arrived. What was needed was not better observation of the present, but better prediction of the future. The answer emerged from a collaboration between the Ford Instrument Company and the United States Navy that had begun in the 1930s. Hannibal C. Ford and William Newell, working with Navy ordnance specialists, designed a mechanical computer that could perform continuous three-dimensional predictions of aircraft motion. The device used principles that seemed simple in concept but were extraordinarily difficult to implement in practice. The Mark I fire control computer received inputs from multiple sources. The Mark 37 director, mounted high on the ship's superstructure, provided continuous readings of target bearing, elevation, and range. The stable element, a gyroscopic device installed in the plotting room, measured the ship's roll and pitch. The pitometer log measured the ship's speed through water. An anemometer measured wind speed and direction. All of these inputs fed into the computer electrically through synchro motors. The computer's genius lay in what engineers called tachymetric target motion prediction. The device did not simply note where an aircraft was at one moment. It tracked the rate of change in bearing, elevation, and range over time. By measuring how quickly these values were changing, the computer could extrapolate forward, predicting where the target would be at any point in the future. The mechanism used mechanical rate integrators, devices that combined position and time measurements through precision gears and cams. These integrators performed continuous calculus, taking derivatives and integrals of motion vectors in 3 dimensions. The computer maintained an internal model of the target's motion, updating this model dozens of times per second as new information arrived from the director. The process worked through a feedback loop. As long as the director tracked the target, mechanical clutches inside the computer remained closed, allowing the director's movements to drive the internal calculating mechanisms. The computer generated predicted values of where the target should be based on its current motion model. These predictions fed back to the director as aided tracking data. If the predictions matched observation, the model was accurate. If they diverged, the computer adjusted its internal state to converge toward the true target motion. When the target maintained constant course and speed, the predictions became remarkably accurate. The computer could predict position up to 30 seconds in advance with precision measured in mils, angular measurements where 1 mil equals approximately 1 yard at 1,000 yards of range. This predictive accuracy enabled a revolutionary approach to anti-aircraft gunnery. The convergence process itself required time that varied with range. At 30,000 yards, the time constant the period required for the computer to reach a stable solution approached 14 seconds. At 2,000 yards, the time constant dropped to 2 seconds but caused unstable oscillations in the output. This limitation meant the system worked best at medium ranges, where convergence was fast enough to be useful but slow enough to remain stable. Against dive bombers attacking from directly overhead or kamikazes diving from close range, the convergence time became problematic. The National Defense Research Committee investigated the Mark 37 system's performance in 1944 and uncovered additional complications. The modifications made to adapt the Mark I rangekeeper, originally designed for surface gunnery, to anti-aircraft use, had introduced errors in the corrections for ship roll and pitch. These errors were particularly severe aboard destroyers, which rolled heavily in rough seas, and at the high elevation angles needed to engage dive bombing attacks. The system that appeared perfect in theory carried systematic errors that degraded performance under exactly the conditions where it was needed most. Yet despite these limitations, the Mark 37 represented an enormous advance over earlier fire control methods. Ships equipped with the system could engage targets that would have been impossible to track manually. The director's radar could acquire targets at ranges exceeding visual range. The computer could maintain firing solutions against multiple targets, switching between them faster than human calculators could manage. The automated pointing of guns eliminated human errors in training and elevation. The system was not perfect, but it was substantially better than anything that had come before. The computer did not simply tell the guns where to point at the present moment. It calculated where to point the guns so that shells and target would arrive at the same point in space at the same instant in time. This required solving a complex ballistic problem. The shells followed parabolic trajectories influenced by gravity, wind, and the rotation of the spinning projectiles. The computer added corrections for all of these factors, plus parallax compensation because the guns were often located dozens of feet from the director's line of sight. The Coriolis effect, caused by Earth's rotation, also required compensation. Firing east or west at high latitudes introduced deflections that could cause misses at long range. The computer incorporated tables of Coriolis corrections based on the ship's latitude and the firing bearing relative to true north. Even the Magnus effect, the tendency of spinning projectiles to curve in flight, required compensation based on the shell's rotation rate and velocity. Every one of these factors was calculated continuously and automatically. The output from the computer was line-of-fire data, bearing, elevation, and fuse time. This data transmitted electrically to the gun mounts through synchro motors. Hydraulic servos with excellent dynamic accuracy positioned the guns precisely according to the computed solution. The fuse time setting told the shell when to explode. Once the system achieved lock on a target and the computer converged its predictions, it produced continuous fire control solutions that updated automatically as the target maneuvered. By early 1942, the Mark 37 gun fire control system had been installed on destroyers, starting with the Sims class, with one system per ship. Cruisers carried 2 or 3 systems. Battleships mounted up to 4 complete systems. The Mark I computer, combined with the Mark 37 director and 5-inch 38 caliber guns, gave American ships the most advanced anti-aircraft capability in any navy. But there remained a critical weakness. All of this sophisticated prediction was useless if the final step, the timed fuse, failed to detonate the shell at precisely the right instant. And timed fuses were notoriously unreliable. They required perfect range estimation. They contained mechanical clockworks that could vary by fractions of a second. Even when everything worked correctly, the shell had to explode close enough to damage the aircraft, and combat aircraft were moving targets that could change altitude in the seconds between fuse setting and detonation. Statistics from early 1943 demonstrated the problem. Ships equipped with Mark 37 systems and firing timed fuses required approximately 2,000 rounds to destroy a single aircraft. Even with the most advanced fire control system in the world, even with perfect prediction of target motion, the weak link remained the fuse itself. A shell could arrive at exactly the predicted intercept point but explode too early or too late to inflict damage. The margin for error was measured in tens of feet and fractions of a second. The solution had been under development since August 1940. Merle Anthony Tuve, working at the Department of Terrestrial Magnetism at the Carnegie Institution, led a project designated Section T of the National Defense Research Committee. The objective was to create a fuse that would detonate automatically when it approached close to a target, eliminating the need for perfect timing. The device became known as the VT fuse, the letters standing for variable time, a deliberately misleading designation meant to obscure the technology's true nature. The VT fuse was, in essence, a miniature radar system installed in the nose of an artillery shell. It contained a radio transmitter, broadcasting continuously, a receiver detecting reflected signals, electronic circuits that analyzed Doppler shift in the returned signal, and a detonator that fired when the frequency shift indicated proximity to a target. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter. All of it had to survive the forces generated when the shell was fired from a gun. Those forces were extraordinary. A 5-inch shell experienced acceleration of 20,000 times the force of gravity during firing. For the fraction of a second the shell traveled down the barrel, every component weighed 20,000 times its normal weight. Standard radio tubes, the only electronic components available in 1940, were designed to survive 10 gravities at most. At 20,000 gravities, a 1-ounce tube would weigh 1,250 pounds. The glass envelopes would shatter, the delicate filaments would break, the entire mechanism would be destroyed before the shell even left the gun. Section T solved this problem through revolutionary engineering. They developed miniature vacuum tubes with rugged construction. The tubes used planar electrodes instead of wire grids. The components were packed in wax and oil to equalize stresses during acceleration. The entire assembly was designed to withstand forces that would destroy any other electronic device of that era. The fact that this technology was successfully miniaturized and hardened for use in artillery shells represented one of the great engineering achievements of the war. January 5, 1943, Kula Gulf, Solomon Islands. The cruiser USS Helena came under attack by Japanese dive bombers. Lieutenant Deke Parsons, the naval ordnance officer who had shepherded the VT fuse project and personally delivered the first combat fuses to the Pacific, stood aboard Helena as the ship's 5-inch batteries engaged the attackers. The guns were loaded with shells, equipped with VT fuses. The fire control was managed by the Mark 37 system with Mark I computer providing predictive solutions. Helena's aft 5-inch battery tracked a Val dive bomber that had just completed its attack run and was turning away. The Mark 37 director measured bearing, elevation, and range. The Mark I computer calculated the lead angles based on the target's current motion vector. The guns elevated and trained to the predicted intercept point. 2 salvos fired. Shells equipped with VT fuses screamed toward the fleeing aircraft. The first salvo passed close but not close enough. The second salvo converged on the target. One shell's VT fuse detected the reflected radio signals from the bomber's metal structure. The Doppler shift reached the threshold frequency, indicating proximity within lethal radius. The detonator fired. The shell exploded 30 feet from the aircraft. Shrapnel tore through the Val's engine and cockpit. The bomber erupted in flames and fell into the sea. The pilot never understood what killed him. Neither did Japanese commanders who analyzed the wreckage. The shell had not struck the aircraft directly. It had exploded nearby, triggered by a mechanism the Japanese could not identify and would not understand for the remainder of the war. This was the first combat kill by VT-fused ammunition, and it demonstrated what would become the decisive advantage in naval anti-aircraft warfare. The combination of predictive fire control and proximity fusing transformed the mathematics of aerial combat. The Mark 37 system calculated precisely where an aircraft would be seconds into the future. The guns fired shells to that predicted location. The VT fuse ensured detonation when the shell passed close to the target, regardless of small errors in range estimation or changes in target altitude. The system eliminated the 2 weakest links in anti-aircraft gunnery: human prediction and mechanical timing. Statistics from combat operations during 1943 demonstrated the transformation. Ships equipped with Mark 37 systems and firing VT-fused ammunition required approximately 500 rounds per aircraft kill. This represented a 4-fold improvement over time-fused ammunition fired from the same fire control system. The improvement came entirely from the fuse technology. The prediction was already excellent. What changed was the reliability of detonation at the predicted point. Against kamikaze attacks, where aircraft flew relatively straight trajectories toward their targets, the improvement was even more dramatic. The predictable motion made the Mark I computer's calculations especially accurate. The VT fuse compensated for the rapid change in altitude as kamikazes dove toward ships. Combat reports show that VT-fused ammunition required fewer than 500 rounds per kamikaze kill, compared to over 2,000 rounds for time-fused ammunition. The transformation extended beyond simple kill ratios. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The psychological effect on Japanese aviators was profound. Pilots reported that American anti-aircraft fire seemed impossibly accurate, that shells appeared to follow their aircraft through evasive maneuvers, that explosions occurred regardless of altitude changes. What they were experiencing was the result of prediction accurate to seconds and detonation triggered by proximity rather than timing. By 1944, VT-fused 5-inch ammunition constituted approximately 35% of rounds fired by American ships. Those rounds accounted for 50% of all aircraft destroyed by 5-inch guns. The disparity reveals the magnitude of the advantage. Shells with proximity fuses were roughly 4 times more effective than shells with mechanical time fuses, even when fired from identical fire control systems with identical predictive capabilities. The V-1 flying bombs launched against London in 1944 provided another demonstration. The Allied anti-aircraft defences around London, equipped with SCR-584 tracking radar, M9 gun directors, and 90mm guns firing VT-fused shells, destroyed 74% of Von second entering the coastal gun belt by late August 1944. The rate had started at 17% in June, before VT fuses became widely available. The improvement came primarily from the fuse technology, enabling automatic detonation near fast-moving targets. The mechanics of lead computation remained consistent throughout the war. Fire control computers calculated future positions based on observed rates of change in target motion. The fundamental mathematics did not change. What changed was the reliability of execution. Early systems required perfect timing of fuse detonation. Later systems using proximity fusing merely required that the shell pass within lethal radius of the target. This relaxation of timing requirements transformed theoretical predictive accuracy into practical combat effectiveness. The lead angles themselves were often measured in seconds rather than spatial dimensions. Gunners learned to think in terms of time to intercept rather than angular measurements. The computer calculated how many seconds in the future the shell and target would converge. This became the fundamental metric of fire control. A fast-moving aircraft at long range might require leading by 10 to 15 seconds, meaning the guns pointed at where the aircraft would be 15 seconds into the future. The human mind cannot reliably perform such calculations during combat. The three-dimensional geometry, the continuous rate changes, the ballistic corrections, the platform motion compensation, all of these factors exceeded human processing capability under stress. The mechanical computer performed these calculations flawlessly, dozens of times per second, producing continuous updates as the tactical situation evolved. The machine thought in futures, not presents. The training required to operate these systems was extensive but not extraordinary. Fire control personnel needed to understand the principles of operation, to recognize when the system was converging correctly on target motion, to identify malfunctions and switch to backup modes. They did not need to understand the detailed mathematics. The computer handled that automatically once provided with accurate input data. The system represented human-machine teaming, where each component contributed what it did best. Humans provided observation and tactical judgment. Machines provided calculation and prediction. By 1945, the Mark 37 system with Mark IA computer represented standard equipment on virtually every American destroyer, cruiser, and battleship in the Pacific. The computers were manufactured by Ford Instrument Company in quantities sufficient to equip hundreds of ships. Each computer contained thousands of precision gears, cams, servos, and electrical components, all manufactured to tolerances measured in thousandths of an inch. The industrial capacity required to produce these machines at scale represented a triumph of American manufacturing equal to the engineering that designed them. The legacy of these systems extended beyond World War II. The principles of predictive fire control, of measuring motion vectors and extrapolating futures, of automated calculation of ballistic solutions. These concepts became fundamental to all subsequent weapon systems. Modern fire control computers are digital rather than mechanical, but they perform the same essential function. They predict where targets will be and calculate how to engage those future positions. The Mark 37 Director and Mark I computer remained in service through the Korean War and into the 1960s. Some systems were still operational in the 1990s aboard Iowa-class battleships during the Persian Gulf War. The longevity demonstrates the fundamental soundness of the design. Digital computers eventually replaced mechanical computers not because the mechanical systems failed, but because digital systems could process information faster and accommodate more complex scenarios. The VT fuse likewise became standard equipment for all American artillery after the Battle of the Bulge in December 1944. General George Patton described the effects as devastating, noting that German units caught in the open by VT-fused artillery fire sustained casualties that exceeded anything previously seen from timed fuses. The ability to detonate shells at optimal altitude above ground, spreading shrapnel over maximum area, transformed artillery from a suppressive weapon to a truly lethal one. The Japanese never developed equivalent technology. Post-war interrogations revealed that Japanese military officials attributed American anti-aircraft effectiveness to superior radar and fire control integration. Some engineers speculated about radio-controlled shells, but dismissed the concept as technically impossible given the forces involved in gun launch. The idea that individual shells could carry miniaturized radar systems seemed beyond credible technology. This failure of imagination allowed both fire control prediction and proximity fusing to remain operationally secret throughout the war. The human cost of this technological disparity was substantial. Japanese naval aviation lost over 12,000 aircraft during the war. Several hundred of these were destroyed directly by ships using VT-fused ammunition and predictive fire control. Each aircraft represented not just material loss, but trained air crews impossible to replace. The cumulative attrition forced Japan to commit increasingly inexperienced pilots, who fell victim to American defenses at unsustainable rates. The broader significance lies not in the specific technologies, but in the systematic approach to problem-solving they represent. American forces identified the weakness in anti-aircraft gunnery, poor prediction, and unreliable timing. They developed solutions through sustained engineering effort, backed by industrial resources. They deployed these solutions at scale across the entire fleet. They integrated new technologies with existing systems. This methodical approach to military innovation proved more valuable than any single breakthrough. The story of American anti-aircraft fire control is ultimately a story about time, about calculating futures, about predicting motion, about computing where targets would be before they arrived. The machines that performed these calculations were marvels of mechanical engineering, but their true innovation was conceptual. They made gunners think in futures rather than presents, in predictions rather than observations, in seconds of lead time rather than angular aiming points. When Lieutenant Commander Wylie watched the Mark I computer calculate intercepts in the plotting room of USS Fletcher, he witnessed the transformation of naval warfare. The machine hummed and clicked, its mechanical brain performing mathematics faster and more accurately than any human mind. The guns elevated to impossible angles, pointing at empty sky. Shells fired into futures computed by clockwork. And Japanese aircraft fell from the sky, killed by predictions they never saw coming. The Japanese never expected American gunners to lead targets by seconds. They never expected mechanical computers to predict futures with precision measured in fractions of a degree. They never expected proximity fuses to detonate shells automatically when passing near their aircraft. The combination of these technologies represented a capability gap that Japanese forces could neither match nor effectively counter. By war's end, American ships fired approximately 70,000 VT-fused 5-inch rounds daily at peak production. The cost per fuse had dropped from $732 in 1942 to $18. By 1945, as manufacturing techniques improved and economies of scale took effect, Over 22 million proximity fuses were manufactured during the war, each containing miniature vacuum tubes that survived 20,000 gravities of acceleration. The scale of production matched the ambition of the technology. The fire control computers that aimed the guns represented similar manufacturing triumphs. The Mark I computer weighed over 3,000 pounds and contained more precision components than most peacetime calculating machines. These devices were manufactured by the hundreds, installed in ships operating worldwide, maintained under combat conditions by trained technicians. The logistics of supporting this technology, spare parts, technical manuals, trained personnel, required organizational capability as sophisticated as the technology itself. Secretary of the Navy James Forrestal stated after the war that the proximity fuse helped blaze the trail to Japan. He noted that without the protection this device provided to surface ships, the westward advance could not have been so swift, and the cost in men and ships would have been immeasurably greater. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitcher commanding fast carrier task forces, recalled that all 5-inch ammunition in 1945 was fitted with proximity fuses, and those fuses knocked down enemy planes by the dozens, preventing ship losses and casualties that would have been enormously larger without this technology. The predictive fire control systems receive less public attention than proximity fuses, but were equally essential to the transformation. Without accurate prediction of future target positions, even proximity fuses would have been far less effective. Shells needed to pass close to targets, which required getting them to the right general location. The fire control computers ensured shells arrived at predicted intercept points. The proximity fuses ensured detonation when targets entered lethal radius around those points. Neither technology alone would have achieved the results. Together, they represented a complete solution to the anti-aircraft problem. The Mark 37 Director and Mark I computer deserve remembrance not because they were revolutionary, but because they exemplified practical problem-solving at scale. The devices worked reliably under combat conditions. They could be manufactured in sufficient quantities to equip the fleet. They could be operated effectively by trained personnel without requiring extraordinary expertise. These characteristics, while perhaps unglamorous, define technology that actually makes a difference in warfare. The lead computation itself, the mathematical prediction of where aircraft would be seconds into the future, represented the intellectual foundation on which all the rest depended. The mechanical computers that performed these calculations translated abstract mathematics into physical motion of gun mounts. The guns elevated to angles that seemed wrong until the future arrived and proved the prediction correct. This transformation of theoretical ballistics into practical gunnery represents one of the quieter but more significant achievements of World War II technology. The final assessment must acknowledge what can be documented and what remains uncertain. Official records confirm that Mark 37 systems equipped hundreds of American warships by 1945. Combat action reports indicate improved accuracy and shorter engagement times compared to earlier fire control methods. Pilot testimony describes American anti-aircraft fire as unusually effective. Statistical analysis shows approximately 4-fold improvement in rounds per kill when using VT-fused ammunition compared to time-fused ammunition. What emerges clearly is that American forces achieved a systematic advantage in naval anti-aircraft warfare through the combination of predictive fire control and proximity fusing. The advantage was not based on a single innovation, but on the integration of multiple technologies. Advanced mechanical computers, radar tracking, gyroscopic stabilization, electrical servo controls, miniaturized electronics, and mass production capability. Each element contributed to a system that exceeded the sum of its parts. For the American sailors who operated these systems in combat, the technology represented tools that improved their chances of survival. The ships they served aboard came under attack by aircraft that intended to sink them. The fire control computers and proximity fuzzes gave them better means to defend themselves. The systems did not eliminate danger or guarantee survival, but they shifted the odds in favor of American forces at a time when margins between victory and defeat were often narrow. The Japanese pilots who encountered this capability never understood the full extent of what they faced. They knew that American anti-aircraft fire was accurate and deadly. They recognized that defensive fire seemed to predict their maneuvers. They noted that shells exploded near their aircraft regardless of altitude changes. What they could not know was that they were flying against futures calculated by machines, engaging an enemy that aimed not at where they were, but at where they would be, detonating shells automatically when proximity sensors detected their presence. The story of American anti-aircraft fire control represents the intersection of mathematics, engineering, industrial production, and tactical necessity. It demonstrates how sustained effort focused on specific problems can produce systematic advantages that accumulate into strategic superiority. It shows that technological innovation matters most when implemented at scale and integrated effectively with existing capabilities. And it reminds us that sometimes the most decisive advantages come not from dramatic breakthroughs, but from solving practical problems well. The Mark 37 Director sits today in museums, its mechanical brain forever silent, its predictions ended. The Mark I computer, with its thousands of gears and cams, rests preserved as a reminder of an era when mechanical calculation represented the cutting edge of military technology. The VT fuses, once produced by the millions, are now displayed in glass cases alongside the vacuum tubes that survived 20,000 gravities to bring them to life. These artifacts represent more than historical curiosities. They represent the moment when warfare became a contest of predicted futures rather than observed presents, when machines began calculating trajectories too complex for human minds, when gunners learned to lead targets not by feet or yards, but by seconds of flight time into futures not yet arrived. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.